In this Part 2 demonstration, I'll be going through an example of applying solver parameters to my model. We'll then use the FO4 in the log file to diagnose the performance. After that, we'll get into another example using the element iterative solver and compare that to the default sparse solver. As mentioned in the last video, we can check our computer resources using the task manager in a Windows environment. Alternatively, we can search for system information, which will tell us how much RAM and processors we are working with. With the system information open, we can see the type of processors being used and the amount of processors. We can also see that there is 1 terabyte of physical memory installed. Now that we understand more of our computational resources, we can start off by reviewing this model. Here we'll start off in the sim, and within it, we can go ahead and turn on our mesh to review our elements. So with the mesh turned on, we can see that it's an all-solid model. It's utilizing tetrahedral elements, and we can take a look at our information dialog box to get a little more information on the node and element count. Now here we can see that the number of elements being used is 3.4 million. The number of nodes is 5.25 million. We're utilizing Tetra 10 elements. We're also utilizing aluminum properties. Now we'll close out of this dialog box and we'll review the constraints. So we're using pin constraints. We're also using a fixed translational constraint along the center hole. And our load consists of a pressure being applied to the very top. We already have our solution all set up. So at this point, we can go ahead and review our solver parameters. And we can see that all the defaults are being used in this case. We can select OK. And now I'll go ahead and I'll edit the solution. We'll make sure that element iterative solver is turned off so that we're utilizing the default sparse solver. We'll go ahead and say OK. And now we can solve the model. And here I'll go ahead and pause the video. So at this point, the model's finished. And now we can go ahead and take a look at our FO4 and log file. So let's go ahead and open up the log file. I like to take a look at the log file first so I can review my solve time. I can see other key information about the run, such as memory, computer resources being used, Scratch directory, and how much Scratch memory is being used, among others. Let's take a look at the very bottom. So this is where we can review our solve time. Here we can take a look at our real time, and that's the wall clock time from start to finish. So here we can see that our run took 3 hours and 25 minutes to complete. Next, we can go ahead and open up the FO4 file. Here we'll be able to check the performance diagnostics. At the very bottom is where we can see our Scratch space usage. In the FO4 file, I like to work my way from bottom up. And two most important values here is going to be our high water Scratch and high water SCR300. We can see that our Scratch, which stores our intermediate data, is a very large number, and our SCR300, which stores our temporary data, is a very low number close to 0. This is ideal, and this is what we want our Scratch to be as well. So with Scratch being a very high number, we can see that we're running out of core and our intermediate data is being written out to our disk. Now let's move about halfway up. And here we'll be able to review our memory usage. Some key parameters here are our minimum memory requirement. This is the bare minimum to run a matrix decomposition. Memory required to avoid spill is the memory required not to spill logic. And memory available gives us insight on how much memory is being used. Now that we were able to diagnose the performance using the FO4 and log files, we can go ahead and adjust the solver parameters so that the model can run in core. We can adjust the solver parameters through trial and error, and this is user specific depending on the model and the problem. So let's start off by going ahead and editing our solver parameters. I'll adjust the memory to 60% of the physical memory. And we'll go ahead and use 12 processors. And finally, we'll adjust the scratch memory from the default of 20 to 50%. So at this point, I'll go ahead and solve the model. And I'll go ahead and pause the video. So the solution has been completed. We can go ahead and take a look at the log in the FO4 file. So within the log file, we can see that the memory has been adjusted since we requested more memory. Scratch memory has been adjusted to 50%. We can also scroll down to the very bottom and again review our solve time. So here we can see a dramatic reduction in the solve time. And now let's go over and take a look at the FO4 file. Within the FO4 file, let's go down to the very bottom and take a look at our scratch usage. So now we can see that the high water scratch and the SCR 300 are both close to 0, meaning that our run was completely in core and we reduce any out of core behavior. Let's review the two runs. The second column shows the parameters and results of the sparse solver using the default settings. The third column shows the optimal run. By doing this, we reduce the scratch so that the model ran in core. The results show a 2.5 times decrease in solve time from 206 minutes to 81 minutes. In summary, we can allocate memory and scratch to keep your model in core. The defaults are good for most problems, but when dealing with larger models with multi-million nodes, you may want to consider reviewing your solver parameters accordingly. Now let's consider a third example. Because our model is completely solid, using solid elements, we can use the element iterative solver versus the sparse solver. The sparse solver is ideal for shell and beam models, but can be sluggish when it comes to large solid models. A good rule of thumb to using the element iterative solver is if your model has more than 80% solid elements. Now going back in the model, let's turn on the element iterative solver. And we'll go ahead and rerun this model. And now I'll go ahead and pause the video. Now the model has finished running, we can go ahead and take a look at the log and FO4 file. So now if we go down to the very bottom, we'll take a look at the solve time for the element iterative run, and we see that it ran in 10 minutes and 55 seconds. Compare that with the sparse run, which ran just over 80 minutes. So we saw an overall decrease by 7 times using the element iterative solver. In summary, we saw how key solver parameters such as memory, shared memory parallel, and scratch memory can be adjusted to optimize solution time. We also saw how for mostly solid models, we can also use the element iterative solver to solve in a fraction of the time as the default sparse solver. Now that concludes our demonstration.